Welcome, Honors Algebra 2, to your first edition of the first Chapter 7 lesson via online for our flipped classroom. The first thing we're going to talk about is 7.1 exponential growth functions. A couple things you want to make sure you have out. First, make sure you have your notes out that I gave you in class, as well as if you could want to take out and pause the video and take out your parent function guide. As you can see on your screen right now, there's one more thing we want to add to the mix, and that is on the third line. There's the exponential graph. And when you look at this, the exponential graph, there's one thing I wanted to make an adjustment with to make sure it aligns with your book. As you see here, the exponential says f of x equals a to the x. Instead of having that, I want to cross that out so you can see I'm in the bottom left corner for the exponential. I just crossed out a to the x. Instead, can you put b to the x? It doesn't make much difference what the actual variables are, but in order for you to make sure that it aligns nicely with what your book is going to say, it's going to be helpful for you to go ahead and do that. Alright, you can go ahead and flip back to your notes. What I want to talk about is exponential growth functions. And what an exponential growth function is another parent function that's very, very popular in the world of math. And for that matter, it's popular in the world around us. You actually use that word a lot. You use the word exponential quite a bit when something's growing exponentially or something's happening exponentially. What's going to happen is it's growing very fast. Exponential means it's growing very, very, very fast, especially if it's a growth function. And so when we talk about that, it's nice to have a math understanding of what that actually means. Before we actually get to the growth part, I first want to talk about what an exponential function in general is. It has the form, as you can see in the middle of the screen, y equals ab to the x. There's two numerical values that are going to be replaced in this value, or in this function. A is just kind of the multiplier. It's that number up front, it's that leading coefficient like we've always talked about with other functions. It's just a multiplier. It either makes something go slower or make it go faster depending upon what that number is. Okay. Also, B is really the number that you're going to grow by. In this case, we can call it a growth factor. We can call it a decay factor when we get to 7.2, but it's another number that's going to be replaced there with the b. X obviously always stays in, but you can see that x is in the power. It's an exponent now, something that we never dealt with before. And so now we're going to have to kind of explore what happens when we put that up in the power. You can see there, for right now, I don't want a to be 0, because if a is 0, you can obviously tell that if a is 0, everything's going to go away. We don't even have a function. And for right now, I want b to be a positive number other than 1. If it's 1, that's kind of boring. 1 to anything is just 1. And so I want any positive number other than 1. For today, because we want to talk about exponential growth functions, I'm looking at that third paragraph. As you might notice, I'm still in the classroom, so still bells going off, and so we might have to deal with that. Sorry about that. There's an exponential growth function, and for this section, I want to make sure that a has to be greater than 0, okay, at least for now, as well as b has to be greater than 1. And let's call b the growth factor in terms of how fast is something growing. So let's go ahead and actually take a look. If we take a look at this, this is actually on page 478, I believe, in your book. If you were to look at this more closely, it's just kind of what a parent function is. You can see here in the middle of the page, you see a graph, a blue-looking graph. Okay, this is what we would call an exponential function. A couple things I'd point out. Okay, first of all, parent functions, especially in growth situations, as long as I haven't messed with the actual exponent itself and the exponent's only x, it's always going to pass through 0, 1. Now you're going to see that changes based on what we do with the exponent, but if it's just to the x power, okay, you're going to see it always go through 0, 1. It's actually kind of a nice little cool little tool that allows me to go ahead and say that. Okay, as you move further and further to the right on the graph, you can see it grows faster and faster and faster. Why? Because you're taking b to a 1 power, b to the second power, b to the third power, b to the fourth power. If b is a numerical value like 2 or 3 or 4, it's like 2 to the first, 2 squared, 2 to the third, 2 to the fourth, 2 to the fifth, and all of a sudden it's going really, really fast and growing very, very fast or growing exponentially. On the left side, you can see it actually gets smaller and smaller and smaller. As a matter of fact, you can see it gets closer and closer and closer and closer to 0. If you were to read the paragraph that's on the left side here that I'm going to outline, and you can if you want to pause it and take a look at this, you're more than welcome to. But more or less what it's saying is that it's approaching an asymptote, kind of like we talked about with the reciprocal function. Okay, it's approaching 0. It's never actually getting to 0. It's never crossing 0, becoming negative. It's just getting infinitely closer, but it's never actually getting there. And then we can talk about domain and range as we go as well. Let's actually talk about one. Okay, let's talk about one of the basic ones, which is y equals 2 to the x. Obviously, one of the easy ways to graph is always to build a table. If that's the last resort that you have, that's the last plan of attack you have, it's still at least a plan. Okay, one thing you can always do to go ahead and make sure you actually get a graph that looks something like we should have. Okay, you can see I put 0 in the middle on that XY table just to go, I want to explore both sides. So let's plug some stuff in. So if I plug in 0 for x, so I have this function up here. I have y equals 2 to the x. If I plug in 0 for x, so I have 2 to the 0 power. 2 to the 0 power is 1. If I go further right, so if I want to plug in 1, for example, 2, then 3, then 4, let's plug in 1. If I plug in 1, that's merely 2 to the first power, which is 2. If I plug in 2, that's really 2 squared, or 4. If I plug in 3, I get 2 cubed, which is 8. If I plug in 4, 2 to the 4th power, or 16. Again, you can hear the bell. You have to kind of work right through it. Apologize for that. If I go the other way, you can start seeing a pattern. If I plug in -1, for example, that's really 2 to the -1. Again, if I go to the bottom right corner, kind of this white space, we should know what that means. 2 to the -1, that's really over 1. Flip it over, that's really 1/2. So I have 1/2 sitting there. Okay, if I do 2 to the -2, well, again, down in the right corner, I have 2 to the -2. That's really 1 over 2 squared, which is 1/4. So when I plug in -2, I get out 1/4. If I plug in -3, take a wild guess. See how they're connecting right now. You can see here that when I plugged in -1, I got 1/2, but then when I plugged in 1, I got 2, 1/4 and 4. -3 and 3, I think that's going to be 8 on one side. If I plug it in, 2 to the -3rd power, I think I'm going to get 1/8. And if I plug in -4, 2 to the -4, when I plug it in, go ahead and flip it, I think I get 1/16, which matches up with its opposite end of 16, just 1 over instead. Let's actually graph this thing. 0, 1, just like the last screen, 0, 1 is kind of that nice base parent function starting point. If I plug in 1, my table says go up to 2. If I go to 2, I should go up to 4. If I go up to 3, I should go up to 8. And quickly already it becomes off my screen, so when I go to 4, it's off to 16. But I have a pretty good idea what the right side of my equation looks like. If I go the other way, I go -1 to 1/2. All of a sudden, I go -2 to 1/4. And then you can see there, I'm already getting so small, it's going to be very hard for me to draw accurately. And so I have a pretty idea of what it looks like. You can see here, as it goes to the right, it's growing exponentially, going off the screen pretty quickly. And as you work to the left, you can see that it actually gets closer and closer to 0. Let's look at the next one. What if I want to graph 3 to the x? You're going to notice I have steps on the right side. I think we'll do that at least initially, and then eventually we'll get to a good enough to a point that we don't necessarily need to make a table anymore. But for the time being, it's not a bad idea to do. So if I look at this, it says make a table. It says use the table to plot the points, and once you have the points, connect them, make a nice little curve. Okay, so let's try and do 3 to the x. In this case, my graph is 3 to the x. So again, make sure you have a pencil and probably a calculator handy. You can pause this at any time to make sure that you do have that stuff handy. I want to plug in 3 to the x. So again, I'll put 0 in the middle. Let's see what happens. If I plug in 0, I think I have 3 to the 0 power. Anything to the 0 power is 1. If I plug in 1, I get 3 to the 1st, or 3. When I plug in 2, I get 3 squared, or 9. Okay, if I go the other way, -1, 3 to the -1, I think that is 1/3. Again, you can justify that by working that on your paper. If I plug in -2, I have 3 to the -2, which I think is 1/9. If I graph that, again, I'm at 0, 1, again, which is kind of nice. If I get 1, I got 3. And if I go to 2, I'm way up here already at 9. If I go the other way at -1, I'm at 1/3, then 1/9, and again, I'm already become so small, it's hard to be accurate on that side of the graph. So again, you can see here that's very much similar. But you can also see if I go ahead and toggle back and forth, here's your y equals 3 to the x graph compared to this last one where y equals 2 to the x. Compare just the right sides. In this one, you can see there's quite a big gap right here for the y equals 2 to the x. As compared to this one on the next one, if my slide's going to go, you can see already that this space right here has been cut off considerably. Okay, so you can see that the bigger that base b, that b in this case, the 3 would be the b value, we'll also call it the base value. Okay, the bigger that is, the sharper it's going to go, because you're going to go 3 squared, 3 to the cube, 3 and 3 to the fourth, whatever it is. But if you do 4 squared, 4 to the third, 4 to the fourth, it's going to go that much sharper up to positive infinity. Well, what if I do this? You had your parent function. Your parent function in this case is y equals 3 to the x. If I go ahead and the only thing different to this next screen is y equals 3 to the x plus 2. Okay, take a wild guess. The plus 2 is inside the operation. Trust it, just like every other parent function that we've had. If it's on the inside, my gut feeling, from what we've learned before, my gut feeling is that if it's on the inside, it's opposite than what we think. I think this thing is going to move my parent function left 2. So if I go ahead and, I'm going to go ahead and write out a table to verify that. Okay, but I'm going to see what happens. So I'm going to do my XY table. I'm on the bottom right part of the screen. If I plug in 0 over here, if I plug in 0, I really have 3 to the 0 plus 2, which is really 3 squared, which is really 9. So immediately I know something's up, because when I usually plug in 0, I usually get 1 out, but now it's been changed. If I plug in 1, if I erase my work at the bottom and start over with 1, I really get 3 to the first power plus 2, which is really 3 to the third power, which is already 27. So you can see it's already going way off my screen only when I plug in 1. So let's go the other way. Let's go further to the left. If I go negative 1, I think that's 3 to the negative 1 plus 2. Again, all I'm doing is plugging in that value in for the x, which is right there. 3 and negative 1 plus 2, which is really 3 to the first power, which is really 3. If I plug in negative 2, again, I'll erase my work. If I had 3 to the negative 2 plus 2, I think I get 3 to the 0 power, rather. And 3 to the 0 power, anything to the 0 power is going to be 1. And you can see here it's getting more slower and slower and slower and getting closer to 0. So if I plug in, for example, negative 3, if I plug in 3 to the negative 3 plus 2, I think that's 3 to the negative 1, which is already at 1/3. So now let's go ahead and graph it and see what's actually going on. When I'm at 0, I'm way up here at 9. I'm not even going to try and plug in at 1 because that's way off my graph. Instead, I'll go to negative 1. At negative 1, I'm supposed to get an output of 3. When I go to negative 2, I'm supposed to get an output of 1. And when I go again, input negative 3, I already get 1/3. So you can see here it's getting closer and closer and closer and closer to 0. And I have a graph that looks something like this. Now, simply watch the screen. Here's the one that I had, and here's the parent function that was before. So you can see here, again, my parent function crossed at 0, 1, and you can see what happened here. If I go ahead and toggle back and forth between here's your parent function and here's what happened with this one, it's exactly the same thing. If I were to sketch in this parent function here, okay, the parent function told me 0, 0, 1, and it was at 1, 3, and it was at 2, it was at 2 was at 9. Okay, you can see here, just by looking at those, if I dot in the parent function, you can already see, I think our guess was right. This, if you look at the 0, 1, it moved over 2. This one right here moved over 2. This one over here moved left 2. So you can, just like we thought, when it's inside their operation, it actually moves to the left 2 or right, depending upon what's on the inside. So again, just like every other parent function, if the number's on the inside, it moves it left to right, and it's opposite than what we think. So let's jump to the next one. At this point, hopefully we're pretty clear as to what we're doing here. If we look at this, again, the plus 2, I think this is still the same as before, so I have left 2. But I think now this minus 3 is on the outside. Okay, it's not being affected by the actual operation of the power. So now if I look at this minus 3 right here, I think that's going to go ahead and tell me, just like before, up and down. Okay, in this case, up and down is going to take me down 3. So my guess would be, if I were to sketch in the parent function is, and I'll put it over here on the far left side, my parent function is y equals 3 to the x. If I were to go ahead and sketch that in, when I plug in 0, I get 1. When I plug in 1, I get 3. When I plug in 2, I get 9. When I plug in negative 1, I think I get negative 1/3. So I have a graph that looks something like this. Again, this is only my parent function. That's all I'm drawing at this point. And if I were to label, I'd say, hey, this is y equals 3 to the x. I think I'm going to take every one of these points. Okay, I'm going to take this one right here. I'm going to take this one right here. I'm going to take this one right here. Okay. And I'm going to go ahead and do exactly as it tells me to do. In this case, it tells me to go left 2 and then down 3. So if I take a look here, I'll take the one at 0, 1. I'll go left 2, 1, 2, and 1, 2, and then down 3, 1, 2, 3. There's my new point. Again, if I do the same thing with this, the next one over at 1, 3, I'm going to go left 2, 1, 2, and then down 3, 1, 2, 3. Kind of gets a little bit messy here. I'll erase the parent function in a second. And if I take the one on the far right, which is 2 at 9, so I'm going to go left 2, 1, 2, and then down 3, 1, 2, 3. I think my next point is going to be right there. So if I erase all this other stuff, just so I can be a little bit more clean with what I'm doing here, I think I have a graph that looks something like this. But now notice something. You can see now my graph is getting closer and closer no longer to the x-axis. It's now getting closer and closer to really y equals -3. You might ask yourself why? Why is that the case? Well, you know that my whole function was moved down 3. I did have a function right at the x-axis, but because I moved my whole function down 3, the asymptote has to come with it, so my asymptote also was going ahead and shoved down 3 as well. So in general, okay, if you look in front of the screen, in the middle of the screen, it says in general. There's really 2 bullets I want you to live by. It's something that we've already learned. This reinforcing exactly the same thing we've already talked about. If a number is in the power, the function moves left and right. For example, if you look at the example that's provided, y equals 5 to the x plus 3, you can see the plus 3 is on the inside of the power. It's actually part of the power, so I know this one's going to move it left or right. It's opposite than we think, so instead of moving it right 3, we actually move it left 3. The next bullet says if a number is on the outside of the power, the function moves up and down. So you can see here this plus 3 is not being affected by the power. I'm just taking the result and adding 3 more to it. So instead, I'm going to move it up 3. And then the last 2 just simply say, hey, what happens when there's a negative up front? We should already know what that means. Okay, when we talk about a negative, if we have a negative leading coefficient, what happens with my graph? And similarly, in the 4th bullet, it says what happens if the leading coefficient is a value other than 1. Okay, what happens when we have that number, that multiplier out front? What's going to happen to my graph? So let's do a couple more and we'll call it a day. For example, what if I do y equals 1/3 times 3 to the x? Let's build myself a table. I'm going to go ahead and be on the right side again. Let's see what happens. I'm going to plug in 0, just kind of get a starting point, see where I am. So I plug in 0, I get 1/3 times 3 to the 0, which I think is really 1/3 times really 1, and 1/3 times 1 is 1/3. What if I plug in 1? Let's go further to the right, see what happens. If I plug in 1, I think I get 1/3 times 3 to the first power, which is really 1/3 times 3, and I think 1/3 times 3 is 1. And then let's keep going. Let's go and do 2. 1/3 times 3 squared. 1/3 is really times 9 then. And I think 1/39 is 3. And let's go one more, see what happens. Let's plug in 3, see what happens. 1/3 times 3 cubed. And I think 1/3, I think 3 cubed is 27. And 1/3, 27 is 9. That's good. That should be a pretty good idea of what it looks like on the right side. Let's go to the -1. If I go to the -1 side, I think I have 1/3 times 3 to the -1. And you know 3 to the -1 is really 1/3 to the first power. And I think 1/3 times 3, I think, is 1/9. So you can already see it's getting pretty small pretty quick. So if I do -2, let's do one more. So let's do 1/3 times 3 to the -2. We know that 3 to the -2 is really 1/3 squared. And we know that 1/3 is really times 1/9 then, because 3 squared is 9. And then when we multiply these, we multiply straight across. And so when we do that, I think we get 127. So getting pretty small in a hurry. Let's graph it. When I plug in 0, I get 1/3. So all of a sudden already it's no longer at 0, 1. It's been deflated. It's been reduced by a factor of 1/3. Okay, when I plug in 1, I get 1 out. When I plug in 2, I get 3 out. When I plug in 3, I get 9 out. And the other way, it gets pretty small pretty quickly. -1 is -1/9, -1/27, closer and closer and closer and closer to 0. So what happens? If I throw a 1/3 out front, okay, you can see it takes longer for the function to get going. It takes longer for it to grow exponentially. Where it used to be, if the parent function was right here at 0, 1, and at 1, 3, and then at 2, 9, you can see it's just taking longer for the x to affect and actually go ahead and make that thing go up to infinity faster. So if the number is less than 1, it's obviously going to be the case. Obviously, if you go ahead and do it the other way, that also might do the same thing. Now, we'll talk more about it tomorrow in class, but if you take a look at this, I have the only thing different I have out front here is a negative. Take a wild guess. If it's a negative, okay, if it's a negative out front, folks, we are going to flip. Okay, that's the biggest thing. It's going to flip the whole thing over. Okay, notice the only thing I'm going to say is this. If there is a negative out front, we can no longer call it a growth function. It still is an exponential, but it's definitely not a growth function because if you look back at our first slide, okay, that a value had to be greater than 0. Okay, it doesn't have to be 0 or have to be greater than 0, but if it is less than 0, then all of a sudden we no longer have a growth function because now it's growing fast negatively versus positively. What I want you to do for tomorrow is I want you to graph this. I want you to show it to me. So if I look at this, you got to tell me, okay, what's that +2 mean? What's this +1 mean? What's this 2 out front going to do to it? And then what's that negative also going to do, like we said, is flip. Also, domain and range. Domain, remember, what's my inputs? What's my biggest x inputs that I can handle? And in range, what's my biggest y outputs there I'm going to get? Not the biggest, but what are all the possibilities of the range that I'm going to get? Okay, and we'll also solidify that tomorrow in class. Hope you have a good night. Go ahead and make sure you fill out your notes, and I'll see you tomorrow morning. Good luck.